China's Centrifugal Hypergravity and Interdisciplinary Experiment Facility, Hypergravity Frontier. China's Centrifugal Hypergravity and Interdisciplinary Experiment Facility, or CHIEF, stands as one of the most technically advanced scientific infrastructures ever constructed. Located 15 meters underground in a reinforced 230 square meter circular hall in Hangzhou's future SciTech city, the facility is built around two record-setting centrifuges, CHIEF 1300 and CHIEF 1900, that define the global frontier of hypergravity engineering. The rotating arm at the heart of the system spans 6.4 meters in radius, and when driven to full speed, it can generate gravitational fields as high as 1,500 G. This extraordinary capability allows CHIEF to compress both space and time, enabling researchers to observe geological, environmental, and materials science processes that would normally require centuries or vast physical scales. The scientific principle behind CHIEF is deceptively simple: centrifugal acceleration can mimic enhanced gravity. Yet the engineering required to achieve this at scale is anything but simple. The CHIEF 1300 centrifuge, which became operational in 2025, was initially the world's most powerful, capable of delivering 300 times Earth's gravity to payloads weighing up to 20 tons. Its successor, the CHIEF 1900, engineered by the Shanghai Electric Nuclear Power Group, surpasses every global benchmark with a capacity of 1,900 G-tons. This means it can subject a 32-ton payload to extreme accelerations or smaller samples to the full 1,500 G design limit. For comparison, the long-standing U.S. Army Corps of Engineers centrifuge in Vicksburg is rated at 1,200 G-tons, while NASA's 42.6-meter diameter centrifuge is limited to 30 G and a 2.5-ton payload. CHIEF's combination of high G levels and heavy load capability is unmatched anywhere in the world. The facility's subterranean placement is essential. At full speed, the rotating arm generates enormous vibration and aerodynamic drag. The underground chamber provides the structural mass needed to dampen these forces, while vacuum systems reduce air resistance and specialized wall cooling and circulation systems dissipate the heat generated by friction. These environmental controls ensure that experiments remain thermally stable and unaffected by the machinery's own energy output. CHIEF's scientific power lies not only in its mechanical specifications but in the scaling laws that govern hypergravity modeling. A physical model built at 100 scale, when spun at 100 G, experiences the same stress distribution as a full-scale prototype. A 3-meter model of a 300-meter dam behaves exactly like the real structure when subjected to the appropriate gravitational field. Time also compresses dramatically. Processes driven by density differences accelerate by a factor of n superscript 2. A contaminant plume that would migrate through an aquifer over 100 years can be reproduced in just 3.65 days at 100 G. At even higher accelerations, geological processes that normally unfold over millennia can be observed within hours. The facility's interdisciplinary reach is organized into 6 specialized laboratories, each supported by 18 onboard experimental systems that operate while the centrifuge is in motion. These systems can apply seismic shaking, thermal gradients, or high-pressure fluids during hypergravity operation, allowing researchers to combine multiple extreme conditions simultaneously. In the Slopes and High Dams Laboratory, scaled models of massive hydroelectric structures are tested for long-term deformation and seismic resilience. The Geotechnical Earthquake Engineering Laboratory uses in-flight shaking tables to reproduce earthquake waves under hypergravity, enabling detailed study of soil liquefaction and the behavior of underground infrastructure. The Deep-Sea Engineering Laboratory recreates the hydrostatic pressure found 2,000 meters below the ocean surface and can simulate the impact of 20-meter tsunamis on offshore platforms and wind farms. The Deepland Engineering and Environment Laboratory accelerates the migration of pollutants through geological barriers, allowing researchers to evaluate nuclear waste containment systems over 1,000-year timescales within days. The Geological Processes Laboratory mimics the pressures and gravitational gradients of the deep crust, offering insights into mineralization and reservoir formation. Finally, the Material Preparation Laboratory uses hypergravity-enhanced convection to produce alloys with improved uniformity, strength, and ductility, materials essential for aerospace, nuclear energy, and high-performance manufacturing. CHIEF's emergence has redefined the global hierarchy of hypergravity facilities. While earlier centrifuges in the United States, Japan, and Europe served specialized roles, geotechnical testing, biological studies, or aerospace research, none combine heavy load capacity, extreme G levels, and interdisciplinary integration at the scale achieved in Hangzhou. The facility is a direct product of China's 14th Five-Year Plan, which prioritizes the construction of major national science and technology infrastructure. By providing a domestic platform capable of validating megaprojects such as the Sichuan-Tibet Railway, deep-sea mining systems, and next-generation nuclear reactors, Chief strengthens China's technological autonomy while positioning the country as a global leader in extreme condition science. Yet the facility's significance extends beyond engineering. Hypergravity offers a unique environment for probing fundamental physics, including gravitational time dilation and the behavior of quantum materials under intense stress. Environmental scientists use CHIEF to model coastal erosion, storm surges, and sediment transport under extreme conditions, generating data essential for climate-resilient infrastructure. Even biological researchers benefit from the ability to study microorganisms and cellular structures under gravitational forces far beyond those found on Earth, offering clues about life's adaptability and the physiological challenges of space exploration. CHIEF ultimately represents a new epoch in experimental capability. Its centrifuges, anchored by a 6.4-meter arm, a 15-meter-deep chamber, and a world-leading 1,900 G-ton capacity, are engineering achievements in their own right. But the facility's true power lies in its ability to compress space and time, revealing the evolution of landscapes, materials, and environmental systems with unprecedented clarity. As CHIEF enters full operation, it promises to influence fields ranging from deep-sea engineering to planetary physics, from nuclear waste management to advanced alloy design. It is not merely a machine but a gateway to understanding the forces that shape our planet and the materials that will define the future.